Hey everybody, welcome back. This is CHEM300 and we're continuing chapter 6 today with talking about how to use chemical formulas as conversion factors. So our goal in this section is to learn how to use a chemical formula as a conversion factor. What we're going to be covering is that you can take the formula of a molecule or a compound, and based on the number of each type of atom in that molecule or compound, you can turn that into a conversion factor. So here we have carbon dioxide, CO2. Which means that for every one molecule of CO2, you have 2 atoms of oxygen and 1 atom of carbon. So we could take these ratios and turn them into conversion factors, just what's shown here. For every 1 mole of carbon dioxide, there's 2 moles of oxygen. Could also say for every 1 mole of carbon dioxide, there's 1 mole of carbon. So you can use the chemical formulas and the ratios of the atoms within a molecule or compound to write a conversion factor that relates a single element to the entire molecule or compound. So just a quick review of what we've covered so far, some of the main concepts. In the very beginning, we talked about Avogadro's number. Avogadro's number is abbreviated N sub A. What it means is that there's 6.022 times 10 to the 23rd particles per 1 mole of substance. The mole is the counting unit used in chemistry, kind of like a dozen is a counting unit used in baking. Molar mass we covered, it's the mass in grams of 1 mole of a substance, as units of grams per mole. And then we covered using both Avogadro's number and the molar mass as conversion factors. So in chemistry, it's very, very common to, in the lab, be weighing out the substances that you're working with in terms of grams. But then when we're looking at chemical equations and reactions, we're interested in the numbers of molecules and atoms. And since we can't count atoms and molecules one by one in the lab, they're so tiny, we take the mass and then we use conversion factors such as the molar mass and Avogadro's number to convert from how much we weighed to how many atoms or molecules we have there. We're going to extend that by now being able to also convert from number of atoms or molecules to numbers of atoms or molecules of a substance using the chemical formula as a conversion factor. So to kind of conceptualize this idea of formulas as conversion factors, we can think of a 3-leaf clover, especially with St. Patrick's Day coming up. So 3 leaves per 1 clover. And so we could write that as 3 leaves per 1 clover using the symbol that means like a ratio. And if we wanted to convert from the number of clovers that we found in a field to the number of leaves, we could set that up as a conversion factor. For every 1 clover that we picked in a field, there's 3 leaves on that clover. So let's say we went out and you picked 14 clovers. Well, with 3 leaves per 1 clover, that means you have a total of 42 leaves in that bunch of clovers that you picked. We do this all the time with other things, right? We know there's 8 legs per 1 spider, 4 legs per chair. If we're thinking of a molecule of water, there's 2 hydrogen atoms for 1 molecule of water. It's the same type of conversion system. So a chemical formula conversion factor comes directly and exactly from the subscripts in the chemical formula, right? We had a subscript 2 in H2O, and that's where we get that there's 2 hydrogen atoms for every 1 molecule of water. So if we look at this a little bit deeper, let's think about carbon dioxide. So the formula for carbon dioxide is CO2. That means there's exactly 2 atoms of oxygen for every 1 molecule of carbon dioxide. So we could write that as a ratio. There's 2 oxygen atoms per every 1 carbon dioxide molecule. We could also write that as there's 2 moles of oxygen for every 1 mole of carbon dioxide. And this works going from atoms per molecules to moles of atoms per mole of molecule, because we can convert between number of atoms or numbers of molecules and moles. We would divide everything by Avogadro's number. And so since everything in the top ratio would be divided by Avogadro's number, the ratios remain the same. The unit changes because we essentially took number of atoms and applied Avogadro's number to convert it to moles. We took number of molecules and applied Avogadro's number to convert it to moles. But since we were using the same scale, the same conversion factor to go from atoms to moles and molecules to moles, they both use Avogadro's number, the ratios remain the same. So if there's 2 atoms of oxygen per 1 CO2 molecule, it means that there's also 2 moles of oxygen for every 1 mole of CO2. So we can write these out as conversion factors. So let's do some practice continuing with carbon dioxide. So if we want to look at the conversion factor to convert between number of carbon atoms and molecules of CO2, that would be that there's 1 atom C per 1 molecule CO2. And conversion factors can always be written as 2 ratios, and we could display this as moles, which I'm going to backtrack and display this as moles. We could also say there's 1 mole of C per 1 mole of CO2. And again, we can go from atoms and molecules to moles, because to do that conversion, you would divide everything by Avogadro's number. Okay, so our first ratio, this is a conversion factor. We want to write it as 2 different ratios. We could say there's 1 mole of C for every 1 mole CO2. We could also say for every 1 mole of CO2, there's 1 mole of C. So I'm taking our general conversion factor with the equal sign and writing it as the 2 possible ratios. Let's do the same thing with the oxygen found in carbon dioxide. So here, from the chemical formula, we have 2 moles of oxygen for every 1 mole of CO2. So we could write that as 2 moles of oxygen for every 1 mole of CO2. Or we could write that as for every 1 mole of CO2, there's 2 moles of oxygen. So I just want you to get comfortable with writing these conversion factors, with recognizing that from a chemical formula, you can write conversion factors for every element in that chemical formula as they relate to the molecule as a whole. So we wrote conversion factors for carbon, and we wrote conversion factors for oxygen here. So let's use some of these chemical conversion factors to solve some chemistry problems. So how many moles of nitrogen are in 45 moles of caffeine? And I give you the chemical formula for caffeine. So here we're given that we have 45 moles of C8H10N5O2, and we want to find moles of just nitrogen. So our plan is to go from moles of caffeine to moles of an element within caffeine, nitrogen, and we're going to use the chemical formula as our conversion factor. And so from our chemical formula, for every 1 mole of our compound, C8H10N5O2, we can see that we have 5 moles of nitrogen. And that comes exactly from the chemical formula. There's 5 atoms of nitrogen for every 1 molecule of caffeine, which means there's 5 moles of nitrogen for every 1 mole of this molecule. So now if we go to solve this problem, we're going to start with our given 45 moles of caffeine, C8H10N5O2. We're going to use our conversion factor that we derived from the chemical formula. For every 1 mole of our whole molecule, caffeine, C8H10N5O2, there's 5 moles of nitrogen. And if we check our units, just like on any other dimensional analysis type setup, we have moles of caffeine and moles of caffeine canceling out, and we just have moles of nitrogen left, which is what we're trying to solve for. So we're going to take 45 times 5, and I get 225 moles of nitrogen, but I need to go back and check my sig figs. So here, 45 moles of caffeine. This has 2 sig figs. That's because 45 moles of caffeine was potentially calculated by weighing out caffeine on a lab scale and then converting grams of caffeine to moles of caffeine. So that's a calculated value. It's based on like the mass of caffeine that was weighed out. But my mole to mole ratio here based on the chemical formula, this is an exact conversion because chemical formulas only contain whole number ratios of atoms. Atoms are counted values. You can't have a fraction of an atom. So these mole to mole conversions based on chemical formulas, these are exact conversions and you don't need to keep track of the sig figs. They have infinite sig figs. Infinite sig figs. So that means our final answer is only going to have 2 sig figs, limited by 45 moles. So I'm going to round the 2 to a 3. So I get 230 or 2.3 times 10 to the 2 moles of nitrogen, written so that we can very clearly see we only have 2 sig figs there. So key steps in this: identified what we were given and what we wanted to find, and then based on the chemical formula, we wrote a conversion factor to convert between the moles of our compound caffeine and moles of nitrogen within that molecule of caffeine. Let's do another one. So let's find the grams of sulfur and 7.5 moles of gypsum, which is calcium sulfate dihydrate. This is what's primarily used to make sidewalk chalk. So let's find out how many grams of sulfur we would have if we weighed out 7.5 moles of gypsum. So we're given 7.5 moles of calcium sulfate dihydrate, and we want to find grams of sulfur. So our plan, we're going to go from moles of compound to moles of sulfur using the chemical formula. Anytime you want to go from moles of compound to moles of something within the compound, you can use a chemical formula as a conversion factor. And same thing going in reverse. If we were given moles of sulfur, we wanted to know how many moles of calcium sulfate dihydrate that would correspond to, we could take this in reverse. And then we've practiced already. If you have a mole value of a substance, you can convert that to grams using the molar mass. Okay, so from our chemical formula, let's come up with this conversion factor. For every 1 mole of calcium sulfate dihydrate, we have 1 mole of sulfur. And I got that from the chemical formula, that there's 1 S in this molecule. So 1 mole of sulfur for every 1 mole of this compound. So now let's set this up. We have 7.5 moles of calcium sulfate dihydrate. We're going to use our chemical formula as a conversion factor. So for every 1 mole of this compound, we have 1 mole of sulfur. And then we're going to use the molar mass of sulfur to convert that to grams. So every 1 mole of sulfur weighs 32.06 grams. And that's straight from the periodic table. Sulfur is an element, so I looked up the atomic mass and then converted it to grams per mole to apply the molar mass. So if we check how our units cancel, we have moles of calcium sulfate dihydrate and moles of calcium sulfate dihydrate canceling out. We've got moles of sulfur and moles of sulfur canceling out, and we're just left with grams of sulfur, which is what we wanted to find. So I'm going to plug this in. 7.5 times 32.06. And I get 240.45 grams of sulfur. We've got to check for sig figs here. So we have 2 sig figs in our starting value. We have infinite sig figs in this chemical formula conversion, and we have 4 sig figs in our molar mass. So we're going to be limited to 2 sig figs at the end. So I'm going to call that 2.4 times 10 to the 2 grams of sulfur. Okay, let's do another one. This is an extra challenging one. It's a multi-step conversion with chemical formulas. We're going to do this one on the whiteboard, but I'll read it out first so you can start writing it down. So a capsule of extra strength Tylenol contains 5.00 times 10 to the 2 milligrams of acetaminophen. If a person takes 2 capsules, how many carbon atoms do they ingest? The formula for acetaminophen Tylenol is C8H9NO2. So let's flip over to a whiteboard. We'll copy and paste that over and get that started. Here we go. We have a capsule of extra strength Tylenol, which contains 5.00 times 10 to the 2 milligrams of acetaminophen. So if a person takes 2 capsules, how many carbon atoms do they ingest? And you're given the formula for Tylenol, which the active ingredient is acetaminophen, C8H9NO2. So given 5 times 10 to the 2 milligrams per capsule, you're going to take 2 capsules, or the person, and we have the chemical formula, C8H9NO2. Okay, so my starting value that I'm going to be using in this problem is going to be the 2 capsules. The 500 milligrams per capsule, that's a conversion factor that relates number of capsules to mass. So I'm going to save that and use it as a conversion factor in the problem. And the chemical formula I'm going to be using to calculate the molar mass as we go through this problem. So we're going to start with 2 capsules. And we want to find number of carbon atoms. So let's make up a plan. We're going to start with capsules. And then we can use this other value we were given, that there's 500 milligrams of acetaminophen per capsule, as a conversion factor. It relates number of capsules to milligrams. And eventually we want to get to grams of acetaminophen so that we can get to moles. And once we're in moles, we can use Avogadro's number to get to number of atoms, and then eventually get to number of carbon atoms. So we're going to go from capsules to milligrams, using that there's 500 milligrams per capsule. And then we're going to go milligrams to grams using the metric system. And then we're going to go grams to moles of acetaminophen using the molar mass. And then once we have moles of acetaminophen, now we can use the chemical formula to get to moles of carbon. And our last step then, once we have moles of carbon, we get to number of carbon atoms using Avogadro's number. So we've got a 1, 2, 3, 4, 5-step conversion here. So let's start solving it out. So we're given 2 capsules. That's going to be our starting point, 2 capsules. And we're going to use the conversion we were given that relates capsules to milligrams of acetaminophen. So there's 5.00 times 10 to the 2 milligrams per capsule. Acetaminophen. And then we're going to convert milligrams to grams. So there's 1,000 milligrams in 1 gram. And now that we have grams of acetaminophen, we're going to use the molar mass of acetaminophen to convert from grams to moles. So for every 1 mole of acetaminophen, we have to calculate its molar mass based on the chemical formula. And I did this ahead of time because I didn't want the whole problem time to be taken up with calculating formula mass since we've covered that. So when you calculate it out, you get 151.16 grams per mole. So that means 151.16 grams of acetaminophen per 1 mole. And now we're ready to apply what we just learned with chemical formulas. You can use the chemical formula to convert from moles of acetaminophen to moles of carbon. So based on the chemical formula, there's 8 moles of carbon in every 1 mole of acetaminophen. And then our last conversion is one we learned earlier in chapter 6. We're going to use Avogadro's number to go from moles of carbon to number of carbon atoms. So I ran out of space there. Okay, so let's check our units before we plug this into our calculator to make sure we don't need to go back and set anything up differently. So we're starting with capsules, and that cancels out there, capsules and capsules. Then milligrams and milligrams cancels out. Then grams and grams cancels out. Then moles of acetaminophen and moles of acetaminophen cancels out. And then moles of carbon and moles of carbon down there. That cancels out, and we're left with number of carbon atoms, which is what the question asked us to find. So we can be feeling pretty good that we set this up correctly, that our units worked out to give us what we wanted. So now it's time to plug it in. 2 times 500 times 8 times 6.022 times 10 to the 23rd divided by the product of everything on the bottom, 1,000 times 151.16. So I got for my number of carbon atoms in 2 capsules of Tylenol, 3.187. 1 times 10 to the 22nd carbon atoms. We expect a really big number, right? Carbon atoms are really small. We have 2 capsules, contains a decent amount, 500 milligrams of acetaminophen per capsule. So we expect a lot of carbon atoms. So that's a good indication that we set this up correctly. We want to check our sig figs before we finish up the problem. So 2 capsules. That has infinite sig figs because you count capsules, so that's a counted value. 500 milligrams per capsule, that's something that was measured, so it has sig figs we have to keep track of, and that has 3 sig figs. Grams to milligrams has infinite sig figs. It's a metric system prefix conversion. Our molar mass has 5 sig figs. Our formula conversion has infinite sig figs because it's based on counting atoms in the formula. And then Avogadro's number has 4 sig figs. So as we scan through here, my fewest number of sig figs is 3. This whole problem is multiplication division, so that's going to limit my final answer to 3 sig figs. So I end up getting 3.19 times 10 to the 22 carbon atoms. So you can kind of imagine this if you ever take extra strength Tylenol. If you take 2 capsules, which is a typical dose, you're actually ingesting 3.19 times 10 to the 22nd carbon atoms in that acetaminophen when you take it, which the commercial name for that is Tylenol. Okay, let's jump back to PowerPoint. And you can check your answer here, 3.19 times 10 to the 22 carbon atoms. Okay, so that wraps up the section on using chemical formulas as conversion factors. Next time, we're going to talk about mass % composition of compounds. I'll see you then. Thanks, everybody. Bye.